My name is Sunny Dragunov. I head the water division at Three-Phase Power Systems. We cover water, wastewater, irrigation, and marine applications. And today we're going to be discussing VACON 100 Flow, a sub-brand of Danfoss. And we're going to be talking about what separates this drive and what makes it unique for applications such as pumping and fan applications. Today we're going to focus about pumping, and we're going to be discussing VACON 100 Flow. Now, right off the bat, when Danfoss was designing this drive, they didn't spare any expense. They covered everything that would make a drive potentially fail, and they addressed all of these issues right off the beginning. Namely, one of the best features that we need to discuss for the VACON 100 Flow is the hardware. Hardware is different than every other drive on the market. The software that has been perfectly crafted has addressed every issue that a pump might require. And we're going to go through that shortly here, but what I wanted to briefly discuss here is the hardware. This is the heart of every drive, is what it's made of, the components that are inside the drive, and what makes it unique, and what prolongs the lifespan of drives and in the end motors as well, how they're protected. First of all, to discuss the hardware of VACON 100 Flow. One of the, should I say, best features about this drive is the fact that it has replaced the electrolytic capacitors with thin film capacitors that can be found in the 100 Flow. Thin film capacitors on the DC bus, they do not dry out like electrolytic capacitors. There is a fantastic thing about these thin film capacitors, that if you leave a drive on a shelf traditionally and it's not being used, electrolytic capacitors would dry out, and then a drive cannot be used. This is as simple as it gets. So how Danfoss addressed this is by replacing the electrolytic capacitors of traditional drives with thin film capacitors. We can leave these drives on storage as a spare on a shelf for years, and the capacitors will never dry out. And the lifespan of these capacitors is up to 10 times as long as electrolytic capacitors. Now, this is the first issue that is being addressed. The second fantastic feature inside is sometimes we put drives, as users of variable frequency drives, we can put them outside. We can put them in areas where there is condensation, there is sudden changes in temperature. And one of the things that happens on a minimized micro level inside the drive is condensation builds up inside the drive. So what happens is potentially there is these little circuits on the control boards can short circuit. So what VACON has done, and Danfoss in the design of these drives, is they have actually varnished all the components and boards inside the drive. So what this makes the drive is protected against environmental elements, against condensation, and this is one of the other things that makes traditional drives fail, would be the fact that the boards are not varnished. So what others consider an option, VACON and Danfoss considers mandatory and standard. So all of these things would come standard with the drive. The other fantastic thing about the VACON 100 Flow is the fact that it comes with an EMI RFI filter inside the drive, EMC filter, which traditional drives, when they run, they emit noise, and because of this noise there could be some potential 4 to 20 milliamp analog signal interference, which is inherently eliminated with the VACON 100 Flow. There is also the next thing that we're going to discuss here is the fact that between drives and motors sometimes there is load disconnect switches, and these cannot be operated under load. So for traditional drives, most often than not, auxiliary contacts on this motor disconnect switch are required that would take out a drive, an auxiliary external fault, so that the drive will not work if the motor disconnect switch is operated. In the case of the VACON 100 Flow, we have automatic protection, a setting inside the drive that can tell the drive that there is a motor disconnect switch, and it simply would slow down and speed up if this switch should be operated under load. So the drive is very unique and smart in that respect. In addition to this, this is when it comes to hardware. It's just beautiful. We have 600 volt, 690 volt drives, 480 volt, 380 volt, 240 volt, 208 volt drives, single phase drives. Every low voltage range has been covered with these drives, and we use them everywhere for all sorts of pumping and fan applications. They're just great. The other thing that I wanted to discuss is that the software inside this drive is very unique. Now, what separates this software from these drives to others is the fact that we have a pump controller inside the drive, and we don't need a pumping relay. We don't need these external components that are traditionally used for other regular drives. Now, I would like to point out the keypad of this drive and the fact that how the software that's crafted, it's beautifully crafted, makes it so easy for the user to use. And an end client loves this kind of drive because everything is so seamless. It's intuitive. Just imagine your smartphone. You have very, the learning curve for this drive is almost zero. You will see in the next video that we're going to show you how to start it up and to do a startup and commissioning on your own. It's very intuitive. You'll find out shortly how this is done. But first I wanted to point out on the keypad, the main thing about the software is how easy it is even to monitor and to operate. When you look at the keypad here, I want to point out that most drives you have to scroll through in order to navigate and monitor different values. Now with this keypad, we can actually monitor up to 9 different things all at the same time. We can monitor 4, 6, or 9 things all at the same time, depending on the matrix on the screen. But here is an example. This is a traditional example. We have, for example, a pumping application. And what are the things that are important for the client to monitor? We want to monitor output frequency. We want to know how fast the motor is running. Great. We want to monitor what the pressure feedback is and what our set point is. The drive actually displays PSI. It can display any number of different monitoring values, flow, pressure, temperature, you name it, we can monitor it. We want to know what the feedback of the pressure is doing in terms of the analog 4 to 20 milliamp input, which can be found in the third spot here. We want to know if the drive is asleep. We want to know if the drive can soft fill our pipes. It actually tells you directly on the screen the status of the PID loop. Then we can also display the motor current as well. In this case, the DC link voltage, it's going to tell us information about the input voltage, which is fantastic. We can also monitor the digital inputs. If we have any selector switches, we can actually monitor their status if they're off or on. This is displayed in this position on the bottom left. We can also monitor the power on time. So a lot of other drives that have external meters, timers, and selector switches, now all of that has been eliminated because everything can be monitored from the keypad. Now here is this example of the power on time. And if we want to flush the lines, we can also monitor that. Now, this is just an example. This is a tip of the iceberg of what is capable to be achieved with this unbelievable drive. The fact that most drive applications require many external components in order for them to work, such as line reactors, EMI, RFI filters, manuals to operate and to troubleshoot and to program, things like RTD relays or thermistor relays, communication protocols such as Ethernet, Modbus, TCP, so on and so forth. Everything actually has been embedded in this drive. We have communication on board, the most modern and fast communication, Ethernet, Modbus, TCP/IP, Profinet IP, and others directly built into the drive. And this simplifies things. Before we had so many components outside of the drive, now everything is inside. So this makes it much, much easier and simpler for clients to operate and use the drives. Beautiful, beautiful. The other thing is if a drive is traditionally operated by a PLC may fail. And traditionally what is being done with PLCs is they tell the drive to run at a predetermined speed if the PLC, the main computer, fails. So this drive, the 100 flow, has a potential of having its own PID controller directly inside. And some of the things I want to list that are special about this drive is that we can mimic what the PID controller can do. Namely, when a pump starts, we want to be able to soft fill the pipes if we have our own PID controller inside the drive. We want to control the pressure of a pipe, we want to control flow, we might want to control temperature, so on and so forth. Let's imagine we're controlling pressure in a pipe. When we start the drive, we could tell the drive to slowly fill the pipes. So we have a mode inside called soft fill. We have another capability that we're going to go through at training time. We can detect if the pipe is leaking. For example, if we're pumping water in a pipe and there is leaks, we can detect when that happens and we can alert and alarm the owner or the operator of the drive very, very easily. We can also control a jockey pump. We could do a pre-charge. There is many other different things that this drive is capable of without the necessity of a pump control relay or a PLC. So the combination of all of these features makes this drive unbelievably simple to use. And when we're starting it up in the next video, you will see, if you know nothing about drives, it will tell you exactly how to use it, word by word. You will see how easy and seamless it is, and the learning curve is zero. One of the greatest features about this drive. And this is why we do not need a manual. This drive is designed with the idea that you do not need a manual to operate it or to program it. And we'll demonstrate why this is. If there is any fault that ever occurs with this drive, we will see it on the screen, the fault. But not only the fault, traditionally people will go to the manual to find out what the cause of the fault is and how to fix it. This drive will actually tell you the cause of the fault and how to fix it directly on the screen. It is that smart and that easy to use. And this is why we love using it. Any chance, an opportunity, an application we have, VACON 100 Flow is definitely the way to go. Hardware and software is just second to none. The mean time between failures is about 57 years on these drives. They're phenomenal. The DC bus capacitors, we have the EMI RFI filters, the varnish boards, the fact that we have 690 volt drives, so that means that the diodes and the transistors are rated for higher voltage capacitance and tolerance. The DC thin film capacitors, if they get hit by transients, they actually do not get hot spots like the electrolytic capacitors, they actually self-heal. A fantastic technology. There is the new wave, the new way to go, the new designs. This is the first of its kind. It's been around for about 6 to 8 years. It has proven flawless. It's just a fantastic drive and everybody loves it. As soon as they try it, they don't want to try anything else. So this is why at 3-phase power we love the 100 flow. We use it religiously and we recommend it to all of our clients. And this is why we're making this video, to tell people how great this drive is, how easy it is to use, how it's different than other drives, and how it incorporates everything inside the drive that a traditional drive would actually have options for and external components. So we can eliminate a lot of components, a lot of costs by utilizing the 100 flow. And we have displayed this in many, many occasions. So thank you for listening. This is a very short introduction to the 100 flow. In our next video, we're going to talk about startup for a pump and further programming. Thank you. Welcome back. This is Sunny again from Three Phase Power. Just wanted to show you here how the VACON 100 flow runs as an example for a pumping application where the drive is actually the pump controller. We have set it up currently. I just wanted to show you here the drive demo. So this is the VACON 100 flow demo. I wanted to show you the different parts of it. This is the drive itself and the keypad. This is the digital inputs that we have, 6 of them. We have a couple of analog inputs here, a motor that will be spinning shortly, and an analog output gauge here. On the keypad here, on the screen, I want to show you what it's programmed for so that when we run it, you'll understand how the keypad and what it shows. Currently, we have output frequency of 0. The drive is not running. We have a 80 psi set point that we want to maintain pressure at 80 psi. The PID feedback is 0 psi, but we can change that with the analog input too. You'll see that shortly. The status of the PID control is stopped. This will tell us if we're soft filling pipes at the beginning. It will tell us if the drive is sleeping. You'll see that shortly. Motor current, this is a very small motor, so the current will be fractional. DC link voltage, this is very important feature to have and display constantly on the keypad because we want to know what the line voltage is. So DC link voltage is fantastic. This slot A digital input 1, 2, and 3. We have off, off, and off. This is the first 3 digital inputs that are being monitored. So whenever 1 is on, if we have a selector switch, a handoff auto, we can utilize digital input 1, 2, 3. And the drive will tell us which one is on and off. Fantastic for troubleshooting, letting you know that your selector switches are actually working or not. And as we do the start command with digital input 1, we'll see the status from off change to on. And it's very great for troubleshooting at any time. The next one is power on time. So this is a elapsed time meter. It'll tell you how long the drive has been running for. It's a fantastic thing. Flushing. We have set up the second digital input if you want to flush the lines at a predetermined frequency. No matter what the drive is running, if you have a selector switch that says flush the lines, we can see how this is going to run shortly. So this is an example here. Let's go ahead and run it and see what happens. So right now we have 0 psi feedback. The lines are empty. So we want to start the motor and see how it goes. So we're going to give it a start command here. So the motor is starting to run. We still have 0 psi and we are, PID status says soft fill. So we're soft filling the pipes at 31 Hertz until we reach to a predetermined level. So we're going to keep increasing the feedback until I believe that was 25 psi. And after 25 psi, we go to 60 Hertz. PID loop starts taking over. So we're running at 60 Hertz. It says PID status is running. Our set point is 80 psi and we see 33. So let's go over 80 psi. So our pressure transducer feedback is climbing, climbing, climbing. We're going to go above 80. So when it's above 80, then the speed starts slowing down. And then we have programmed the drive below 35 Hertz to start a counter. And this counter in our case is about 10 seconds, but to put the drive to sleep. This timer can be any number of seconds that you like. But we want to know when the pressure is too high, when the drive is no longer needed. After a few seconds, the drive will go to sleep. and we're going to demonstrate this shortly. So the speed is slowing down, 39 Hertz. Minimum speed, I believe, for this application is 30 Hertz. So at 35, it went down, so the timer now starts counting. And then we're going to put the drive to sleep shortly here. Here, the drive is asleep. So when the drive is asleep, it's no longer needed. The pressure is too high. Now we want to drop the pressure below 60 psi in order to wake up the drive and have it run again. But if the pressure falls below the 25 Hertz of the soft fill mode, it will actually try to soft fill when it wakes up again. So there is no water hammer. We can demonstrate this by dropping the pressure, and now the drive is running. It's ramping up to 60, and the pressure feedback is 40 psi. Now, while we're running here at 60 Hertz, if we want to flush the pipes, we can activate a second input. And this is activating the flushing sequence of the drive, which runs at 40 Hertz until we want to stop it. So it doesn't matter what the drive is doing. When we activate the flushing sequence with another digital input, it overrides whatever we're doing. So it's really, really good that way. So you can see both of the digital inputs are on. So it's really, really good. Now, we could turn off the drive and let it finish flushing, or we can shut off the flushing, and then the drive will slow down to 0 because the run command is off. And we are going to reset everything back to 0 psi. Hi, welcome. I'm Sunny from 3-Phase Power, and today we're going to demonstrate how to program a VACON 100 flow to run a pump application with a pressure transducer. Okay, so this is the beginning. When you turn on a drive, this is the first screen that you will see, is the language that you need to select. So we're going to go through step by step everything that you see on a drive, and we'll see how easy it is and seamless and very, very, very user-friendly. Let's do this. The language is English. We're going to click OK. US is fine for daylight savings time. Because we have a battery, a real-time clock inside the drive, we can program the date and time inside the drive. So if anything should happen or we want to program when the drive runs, we can actually use this. So there is a battery inside this drive 100 flow, and it's fantastic because of the real-time clock. So many, many benefits come with this, and you will see soon why. So we're going to leave the time and date the way it is, year 2018. Date, you could change it as you see fit. Startup wizard. Whenever we start the drive, we always want to use the startup wizard because it makes things easy for us. So we're going to say yes. Now, here is an application wizard that you can run this drive many different ways. The standard way of running a drive is with a PLC. However, if we don't have a PLC, if we're running this drive standalone on a wall with a pressure transducer, which is the case right now, instead of a standard application, we're going to pass by the HVAC application that we can also run, but PID control. So the drive inside it has a PID controller. So we don't need any external PLCs or pump controlling relays. This is the beauty about this drive. Also, this drive can also run multi-pump control applications, such as one drive can operate and control up to 8 motors. Let me repeat that. One drive can control up to 8 motors. We have a choice with one drive and 7 starters maximum, or one drive and 7 soft starters, or we can have 8 drives altogether, anywhere from 1 to 8. So this is called the multi-pump single drive if we have starters or soft starters, or multi-pump drive, multi-drive if we have multiple drives. For this case scenario, we're going to go with the simple application of PID control of one drive and one pressure transducer. So we're going to go OK. We're going to use an induction motor, so we're going to skip through that. OK. The voltage, please look at the motor nameplate. Most of the information will be on there. So in our case, we have 230 volt motor. We're going to change from 50 to 60 hertz by going left once and then up once. This changes it to 60 hertz. Next is the motor nominal speed. Whatever the RPM on your motor nameplate is, enter it here. The ampacity of the motor. If it's a submersible pump motor, the service factor amps should be entered here instead of the full load amps. Only if you know that the actual pump motor will go into service factor. So this is very important if you're running with this drive a submersible pump application. In our case, we're going to put a motor FLA of this particular motor. It's 1.9. Next thing is the power factor, and then the drive states. This is how the drive makes things simple for us, okay? The drive says the next question are for setting motor min and max frequencies and acceleration and deceleration ramp times. So if we have a submersible pump or some kind of application where we need dual ramp times and dual ramp speeds, we can also program this. So right now we want minimum frequency reference. This could be 0, could be 30, could be whatever you want it to be, 40 hertz. So we'll leave it at 0, but you can adjust it as you see fit. Maximum frequency, we're going to program to 60 hertz in our case. We could go up to 320. Acceleration time, it's asking now. 5 seconds is default. We could change it to 10 seconds by going left here and down to 0. So 10 seconds. Deceleration time, we can leave it at 5 seconds, or we could change it to whatever we like. We can leave it at 5. Application wizard, always yes. Makes our life much, much easier when the drive is asking us what to do. So we'll click on yes, and the drive says the following. The next question is for selecting from where the start and stop command and frequency reference is given. So our drive has a potential of giving the option of a client to start and stop from the keypad, or from selector switches such as handoff autos, or from a communication protocol such as Ethernet or DeviceNet or any other protocol of communication that exists out there. So we're going to click OK, and we're going to select now what do we want. Input-output terminal is the selector switches. Field bus would be your Ethernet or Modbus TCP, and or keypad. So right now we want to demonstrate how the drive runs standalone. Therefore we're going to select keypad because we do not want to operate any selector switches. We want everything to be standalone, a drive on a wall. Very simple. So we'll put keypad. The next thing, it says the PID will be configured for one set point. Remember, we have one pressure transducer, so set point and one feedback. First question gives us the possibility to show another process unit than percentage for PID values. Example, so this drive can display PID bars, you'll see shortly. So we're going to click OK, and we're going to select what we want to monitor on the screen. So it starts with percentage, and most drives do percentages. However, this drive is special, and we can monitor many different things. Here's an example. We're going to scroll through until we find PSI, because this is what we want. So we have liters, temperatures, squared meters, flow, bars we can monitor, kilopascals, temperature in Celsius, gallons per minute per hour, many, many different options. And we're going to focus on PSI, which is right here, PSI. All right, so once we select PSI, the drive says, next question are for setting the range of the sensor. A pressure sensor having a range of 0 to 10 bar would mean that minimal is 0 and maximum is 10 bars. So we're going to click OK. And now we're going to say what is the pressure transducer range that we have. We have 0 PSI as minimal, and maximum by default it's 100. You could change that to 150, 200, whatever you like. So we'll leave it at 100. And then the process units, 2 decimal places is fine, so we'll leave it at that. Next, the drive says the next question is for selecting what to use as a source for feedback signal. Analog inputs or field bus connecting can be chosen. If process data is chosen, a value of 10,000 means 100%. In our case, we're going to set PSI, so it makes things very, very easy for us. Now, analog input 1, 2, 3, or 4, the drive gives us an option of where we want to connect the pressure transducer. So we know that the pressure transducer is 420 milliamps. Therefore, we will plug it in AI2, which is analog input 2. That is the default setting, so we'll just leave it alone. We press AI2. The next, it says next question is for selecting an analog signal range. Please also remember to set the dip switches which are located under the cover in their right positions. Now, what this means is that we have two analog inputs by default, 4 to 20 milliamp and 0 to 10. The analog input 2 is 4 to 20 and the analog input 1 is 0 to 10, where you can connect a speed pot. So what we do here is if you want both of those inputs to be, let's say, 4 to 20 or both of them to be 0 to 10, we could change dip switches. But by default, analog input 2 is 4 to 20 milliamps, so we just leave things the way they are. So we press OK, and we're going to select 4 to 20 milliamp, which is the default selection for AI2. Next, the drive actually guides us, and the next question is for setting what kind of process we're having. If an increase in output frequency means that the feedback increases, we should set error inversion to normal. If feedback value decreases, inverted should be chosen. So we've always, in my experience with three-phase power, we have used normal. We'll just leave it at that. Inverted is very rare, not in our application. So for our case, normal is fine. Next, the drive says, next question is for selection of what to use as source for the set point signal. Keypad, analog inputs, or field bus process. So this basically says, okay, where do we want to program the actual set point from? And logic states, instead of analog inputs, we want to, because we have one drive and one pressure transducer, we want to use the keypad as a source for set point for this pressure transducer. So we're going to scroll down with these arrows until we get to keypad set point 1. And then we select this. So next question is for setting the keypad set point. Basically says, okay, you've selected your keypad, now tell me what is the value of the PID that you need as a set point to be maintained. So it flashes 0, minimal is 0, maximum is 100, because this is what we programmed for a pressure transducer. So we could say we want the pressure set point to be 80 psi. So we're going to go left once and up 8 times. This is how we could get to 80. Okay, 80 psi. Next question. Do you want to configure the drive to go into sleep mode at low demand? The drive stops when the output frequency goes below a defined level and starts again when needed to maintain feedback value at a certain level. Press OK to continue. So, when drive is not needed, we want to put it to sleep. This is the logical thing to do. So we will click yes. So up once, we'll click yes. We want to configure the sleep wizard. So the next question will tell us the two questions, the drive says. Below which frequency and after which delay should the drive go into sleep mode? So this is very important. So if the drive is running at 60 Hertz at full speed and we want to put it in sleep because we have already achieved our set point, we want to start decreasing the speed. And the drive has a timer that we'll program shortly that says after we start slowing down the speed, after which frequency do we want to use the internal timer in order to put the drive to sleep. And we'll see that. So, sleep frequency. Now, we can say for our case scenario that after, when the drive starts slowing down from 60 Hertz, and if our minimal speed, for example, is 40 Hertz of future application, we want to start the counter, let's say below 55 or below 50 hertz. So as an example here, we're going to use below 50 hertz. So below 50 hertz. And for how long? So in our demonstration case, we're going to change the seconds to 10, but in real life you can program it whatever you like. In the sleep frequency, you could change it to 40 hertz, 45, whatever the application demands. So we're going to click OK, and then the drive says, next question, at which level in feedback value should the drive wake up again? So now let's think about this. The drive is asleep because we have achieved over 80 psi. Then the drive is asleep. So now when do we want it to wake up? 70 psi, 60 psi, this is depending on the application. In our case scenario, the default value is 72, but we can put it to 60 psi. So set point at 80, wake up level at 60 psi. After completing the wizard, navigate the keypad control page by pressing function button, which is this button here, and select control page. Press OK to continue. So we're pressing OK. So this is it. We have programmed the drive. Now we have programmed the drive. We've completed the steps. The wizard is finished, and we want to actually run the drive. So when we run the drive, we want to go into multi-monitor menu. So this is the main menu of the drive. It's very, very intuitive, and we'll go through it right now. Quick setup is the wizards that we went through right now. Monitor is where we want to go when we run the drive, because we want to monitor different values. We want to see where the PID is. We want to see the speed. We want to monitor what's happening, voltage, and etc., etc. So this is the monitor. Parameters is where we want to program additional parameters, which we will go into shortly, and so on and so forth. So to keep things simple, let's go into monitor and multi-monitor. So multi-monitor, this is key, because by default, the drive lets us monitor up to 6 things. As you saw in the introduction of 100 Flow, we saw that this drive can monitor up to 9 different things all at the same time, which makes it super simple to use the drive and very intuitive, and you don't need to scroll through menus to view different things, which is beautiful. Right now, by default, the drive displays these values, which is output frequency, PID set point, PID feedback, PID status, motor current, and DC link voltage. For starters, we can leave them alone. But for example, if you want to monitor something else or something additional, such as digital inputs or whatnot, you can select a value that you do not need. For example, we can select the set point, or we can select output frequency. So just for this example, we can choose motor current, because this motor is so small, we don't care for it really. So we can highlight the area that we want to change. You press OK, and then the drive gives you a list of values that you can actually monitor. So it's very user-friendly, and it's right there. You highlight what you want to change, and you scroll down to whatever you need to change. For example, right now, we can monitor, as an example, unit temperature. You can monitor any number of different things. Errors, you can monitor flushing status, reversing status. For example, if we could do auto cleaning, deragging, if the pump allows you to go backwards and forwards to dislodge the impeller. But right now, one of the things that we're just going to pick just to show you how to change it on the multi-monitor is unit temperature. So we click OK, and it gives you the actual temperature of the drive itself, 27 degrees Celsius. So this is an example of how you can change this, and let's run it right now. So when you look at the keypad, in the top left corner, it will tell you if it's stopped or running. The next icon here tells you if the motor is rotating forward or backward. If it's ready to run, it says ready or not, and then the control is from keypad. So if we use the green button here, this gives us a run command. If the stop button is the red button. The function button, if we press it, we could change between local control and remote control, which is selector switches. Or we could change the direction of a motor so that it spins backwards. For example, if the motor is miswired and it's spinning backwards, you could go here and select change direction and the motor will spin in the correct direction. Very, very simply to do. So we're going to leave it at that. We're going to go back. So we have keypad control and PID feedback is with our analog input 2. So we want to run it. So let's press run and the drive will accelerate as we see here, output frequency. And now we're going to start changing the actual feedback. So we're filling up the water pipe here. The PID feedback increases and we want to get this over 80 in order for the drive to slow down. So it's going to go, we're increasing it. And once the feedback goes above 80, the drive immediately slows down. And he runs the counter that we programmed, the 10 seconds, below, I believe, 50 hertz. And now the drive, it says asleep. The drive is sleeping. So if this pressure feedback from 88 drops below 60, the drive should wake up because our set point is 80 currently. So let's decrease it. This value here to below 60 and the drive starts running. So we saw how the drive runs. Now we're going to stop it and program soft fill. What this means is that the PID controller right now, it ramped up to 60 hertz immediately, but we don't want the water pipes to have water hammer. So we're going to program the drive to do a soft fill of the pipes gently to eliminate water hammer, and we'll show how to do that. So let's stop the drive with the stop button, and we're going to reset the PID feedback to 0 psi. So imagine this is the new application. So what we're going to do is go back to the main menu, and we're going to use logic in order to find where the soft fill program is when it comes to the PID controller inside the drive. So here's the main menu. We're going to go down to parameters because this is where everything to do with programming the drive is. We're going to click OK, and then as I'm scrolling down to the PID controller that we want to program, you will see how everything along the way, motor settings for full load amps, start and stop if you want different ramp to stop or coast to stop, speed references, ramps if you want dual ramps, you could go here, input-output configuration. This is one thing that I wanted to quickly mention about input-output configuration is that we can assign different functions to digital inputs, so we can reduce the amount of wiring for digital inputs, which is great. Going down, we're going to go to PID controller. Once we enter PID controller, we're going to find something called soft fill, and this is where we're going to go. So right now soft fill function is disabled. We want to enable it. So here we go. We have two choices. We can soft fill a pipe up to a particular pressure level, or we can soft fill a pipe with up to a predetermined amount of time. So for our case scenario, we're going to choose level, which is up to a particular pressure level. We're going to click OK. Enabled level. We're going to go back once. We're going to say, okay, now when we are soft filling the pipe, what kind of frequency should we run the drive at so we prevent water hammer? We're going to go in here and we're going to edit, and we're gonna say let's run at 30 hertz. So 30 hertz, we want to run at the pump minimum speed until the pressure is, we're gonna go in the next, we're gonna edit this and we're gonna say until the pressure is, so wake up level was 60, so we could say until 35 psi, just an example here. So 30, 3, then 5, till 35 psi, and this is it. We're not going to do the timeout, so if there is any fault, the drive will fault, and this is it. We're going to go back all the way until we get to the main menu, and then we're going to go back to multi-monitor. So this is where we're going to monitor what's happening with the drive. So let's run it, and we have PID feedback 0, so that means the pipes are empty. So let's click on run. The drive says soft fill. So the drive is running right now at 30 hertz until we see 35 psi. Okay, so everything is done automatic. So we're going to increase the pressure and monitor this second value here until we get to 35, and after that the speed should increase to 60. Here we go. So we're above 35 psi. We've gone to 60 hertz because now the pipes are pre-filled, they're safe, there's no water hammer. Let's ramp up. And then again, once we go up to above 80 psi, the drive will slow down and it's going to go to sleep eventually. So we could do the same thing with pipe leakage detection. We could do many different things that make this drive amazing and very easy to use and intuitive. And we can monitor up to 9 things at the same time, so it makes this a pleasure to use. It makes this a pleasure for me to provide it to clients, and I hear great things about it with every single user. So thank you for sticking with me. Thank you for being with me in this training session, and thank you for your time. I look forward to working with you, and give us a call anytime.